Let's investigate the one-dimensional particle in a box. In this model, the universe can be broken up into three separate regions. The middle region, I'm going to call the box, and these two outer regions, I'm going to call impenetrable barriers. So the particle is stuck inside the box. It cannot escape because these are impenetrable barriers. That's what I've shaded in green over here. Now, let's establish a coordinate system. This is the one-dimensional particle in the box. So we only have one spatial coordinate. I'm going to call that x. Now, I'm going to use the convention that x equals 0 is at the left-hand side of the box. And on the right-hand side of the box, we have x equal to a. And a is defined to be the length of the box. So this length is a. The midway point over here can also be used to define the origin. So we could set x equals to 0 right over here at the midpoint of the box. And that, in our coordinate system, is x equals a on 2. You might also see that in different sources. So that's another common convention for a convenient coordinate system. We're actually free to set the origin wherever we want. But this is a far more convenient choice. The choice where you put it in the middle, that is also convenient, but we're not going to use that in this video. So now that we've established the coordinate system, we can use that to define a potential energy function. So inside the box, we can describe that as a potential energy of 0. And outside the box, because these are impenetrable barriers, they can actually have infinite potential. So we can describe that with infinite potential. And how can we actually write that down? Well, we can use a piecewise function. So the potential energy function over here, v of x, this is a function of the spatial coordinate, can be written in this form. This is a piecewise function. So the potential energy is 0 if x is in between 0 and a. So that's this region, the inside of the box. And otherwise, it's infinity. So outside the box, the potential is infinite. So this is the potential energy function for the particle in a box. Now, the particle in the box is sometimes called the infinite potential well, or the infinite square well. And the reason for that name is this potential energy function. So it's just describing the potential energy function. So what do we want to do with this system? Well, we want to find the wave functions that are possible inside here. And we also want to find the energy levels that are allowed. So we want to do all of our one-dimensional quantum mechanics for this particular system. And it turns out that this system is very convenient because we can write down all of the allowed eigenfunctions. So let's have a look at the time-independent Schrodinger equation. That is written in red over here. So this is the time-independent Schrodinger equation. Psi of x is the wave function, and it is an eigenfunction that has a particular energy value associated with it. So you can think of these guys as the eigenfunctions of the Hamiltonian operator. So this over here is the Hamiltonian operator acting on the wave function. And when the Hamiltonian acts on the wave function, it's the same as this guy over here, E multiplying this wave function, because this is a special function. This is an eigenfunction. So this is analogous to eigenvectors and eigenvalues. You can think of this guy as the eigenvalue and this as the eigenvector. But it's not quite an eigenvector, it's an eigenfunction because it depends on a continuous variable. It depends on x, and x can take on any value over here. So one restriction we can put on this wave function over here is that it has to be 0 outside the box. So because this is an impenetrable barrier, we can't get any value for the wave function out here. So this has to be 0. So that's what I've written underneath here. This is the condition that the wave function has to be 0 over here. That's because when we take the square of the amplitude of the wave function, that's going to give us the probability. And we have to have a probability of 0 for finding the particle outside the box. That is one of the fundamental assumptions of this system. The particle has to stay inside this region. So psi of x less than or equal to 0, what region is that? That's this region over here. So if x is less than or equal to 0, that's everything to the left-hand side over here, so left of the origin. This value of the wave function has to always be 0. And that's the same for x greater than or equal to a. So it has to be equal to 0 out over here. And at the edges, at the boundaries, it also has to be equal to 0. That's because of continuity. We need to have a continuous function, so it has to be continuous. And that is actually called the boundary condition. And we're going to be using the boundary conditions a little bit later when we actually find some solutions. So let's go back to the time-independent Schrodinger equation. What can we see is a simplification that we can find in this equation? So over here we have the Hamiltonian operator acting on the eigenfunction psi. So this can be thought of as a stationary state, as we've covered in some of the previous videos in the quantum mechanics playlist. So this over here, this is the kinetic energy part, and this is the potential energy part. And the kinetic energy part has a second derivative with respect to x. So over here I'm writing the total derivative. I'm not writing a partial derivative because we're only dealing with x. As soon as we start to introduce other variables like y and z, this is going to turn into a partial derivative. And you'll see that in the next video. So now what I want to do is I want to simplify this equation. If we're looking at this equation inside the box, then we know that the potential energy is 0. And if the potential energy is 0, that means that this term disappears because this is just 0 and it's multiplying psi, so that cancels out. So we lose that term. So the only terms that we have left are this kinetic energy term and this term over here with the energy. So this is going to allow us to find the allowed energy levels and the allowed associated functions. So let's have a look at what we get. We're going to get a differential equation. And luckily for us, it's a simple, ordinary differential equation. I'm going to write it down over here. So what I'm going to do is I'm going to take this guy over here. I'm going to multiply both sides by this, or actually divide both sides by this. And that's going to turn this guy into a more recognizable equation. So I'll write that over here. So on the left-hand side, I'm going to have the second derivative of psi with respect to position. And I'm going to neglect to write as a function of x. I'm going to neglect to write these little brackets with x, because that is clear in this definition up here, in the time-independent Schrodinger equation. So we have the second derivative with respect to position of psi. That is going to be equal to some constant times psi. And what is that constant going to be? Well, it's going to have a minus sign. We're going to have minus 2me. I've just brought this 2m onto the other side. And I'm going to divide by h bar squared. So that's this h bar squared, and I've divided both sides by that. And what are we multiplying by? We're multiplying by psi. And I can actually write this as a more condensed constant. So I can write that as a constant k. So I'll write this as minus k squared times psi. And here's another thing I'm going to write. I'll write on the side over here, I'll write the definition for k. Now this is a very important constant that we're going to be using later in the derivation. So I'll write that over here explicitly. K, I'm going to define to be equal to the square root of 2me over h bar. I'll write this properly. We have over h bar. So have a look at this. If you take the square of this h bar is going to turn to h bar squared, and this square root is going to go away. So we're going to have 2me at the top. And that's exactly what we need. So have a look at this ordinary differential equation. We have a second derivative equal to minus a constant times the function. What function can you think of that is equal to the negative of its second derivative? So one function I can think of is sine, and another one is cosine. And in fact, the general solution is going to be a sum of sines and cosines. You could also do this with exponential functions, but we're not going to do it with exponential functions. It's actually a lot simpler if we just deal with sines and cosines. And you might recognize this ordinary differential equation from classical mechanics. In classical mechanics, this shows up when you're describing the harmonic oscillator. So if you have a simple harmonic oscillator, you also get an ordinary differential equation of this form. So let's write down the general solution. I'm going to write it down over here underneath. So what we're going to get is psi of x is equal to, so we're going to need some coefficients, some constants, and I'm just going to call them a and b. So we're going to have a times sine of kx, and that k is as defined above, And then we're also going to have b times cosine of kx. So these are valid solutions. Each of these by themselves are valid solutions. And then if we take the superposition or the linear combination of these two guys, that is also a valid solution to this differential equation. So why is that the case? Well, if you take the derivative of sine and then differentiate it again, you're going to get minus sine with a factor of k squared out the front. And that's the same for cosine. If you differentiate this twice, you're going to get minus cosine, and this k is going to come out twice because of the chain rule, and that's going to give you this k squared. So we do get the function multiplied by minus k squared. And that's exactly what we need. You can write this out in full and convince yourself that this is a general solution to this ODE. Now, we have to find what a and b are. These are just some arbitrary coefficients. We have to specify them. So how are we going to do that? Well, we actually have boundary conditions. As I discussed earlier, these over here are our boundary conditions. So at the boundaries, at x equals 0 and at x equals a, the wave function has to be equal to 0. So let's actually take those boundary conditions and use them. So for the first boundary condition, I'm going to take this guy over here. So psi of 0, what is psi of 0 going to be? Well, psi of 0, if I substitute x equals to 0 into this equation, I'm going to get a 0 appearing over here. Sine of 0 is 0. If you remember from the unit circle, sine of 0, that's 0. So this term is going to disappear. Cosine of 0, well, that's equal to 1. So here I'm going to get a 1, and here I'm going to get a 0. So we don't have to worry about this, but we're just going to get b. So b is going to be the only thing that remains. So I just want you to be very comfortable with that reasoning. We've just substituted x equals to 0 inside this general solution of the ODE. And what is that giving us? Well, this vanishes because sine of 0 is 0, and cosine of 0 is 1, which just leaves b. And if we know that psi of 0 is equal to b, and we know that psi of 0 has to be equal to 0, we can conclude that b is equal to 0. So we have gotten rid of this cosine. The cosine can just be ignored because we know this coefficient has to be equal to 0. And why is that the case? Well, it's because of this boundary condition. Let's have a look at the other boundary condition. So let's have a look at what happens when we have psi of a. So we're going to set x equals to a. So that's this right-hand side over here. So what is the boundary condition there? Well, psi of a also has to equal 0, but let's substitute a inside here. So we already know from this boundary condition that b is equal to 0. So we can just ignore this term because we know it's 0. What about this term over here? Well, if we substitute x equals to a, then we're going to get a times sine ka. So I'll write that over here. We're going to get a times sine of ka. So that's what we have. And what does this have to equal? Well, it has to equal 0. So we have two possibilities to make this product 0. Either the coefficient a is equal to 0, or sine of ka is equal to 0. Let's consider the possibility that this coefficient is equal to 0. If a is equal to 0, then both of these coefficients are equal to 0, and the wave function is just equal to 0. That's not a very useful wave function. It's actually not even normalizable. So you can't normalize a function that's just 0 everywhere. So we're going to ignore that possibility. A is going to have to be positive. What about this over here? This is the thing that has to be equal to 0. So we're going to have to set this equal to 0. So this guy has to be equal to 0. Now, what are the values of k that are going to make sine of ka equal to 0? We could set k equal to 0, but that's going to cause the same problem as before. If k is equal to 0, then we're just going to have sine of 0, and that function is always 0. So that is, again, a problematic function. So what we want to do is we want to set k to be a set of values that guarantee sine to be equal to 0. And we want k to be non-zero. So how is that going to work? Well, I'll write that over here. We're just going to get the nth value of k. So we're going to have a set of values. So I'm going to write the nth value of k is going to be equal to n times pi over a. And n is going to be a natural number. So that's 1, 2, 3, 4, 5, and so on. So any natural number is going to satisfy this. So have a look at this. If I substitute this back into this sine expression over here, This a in the denominator is going to cancel with this a, and we're just going to be left with n pi. And n times pi, if you substitute that into sine, that is always going to guarantee that sine is equal to 0. Because if you remember the unit circle, if you go in half, so pi is half a circle, if you go in half circle slices, that's going to guarantee that your vertical component in the unit circle is 0. So if you go 1 pi around, sine is equal to 0. Another pi around, that's also equal to 0. And if you keep doing that, you're going to just jump between the right side and the left hand side of the unit circle. And that is where sine is equal to 0. So cosine is equal to 1 and minus 1 in those parts, and sine is equal to 0. So these are the values of k that are allowed. And this is where the quantum part of quantum mechanics comes into play. We are quantizing this value. And this is actually going to end up quantizing the energy as well. What about A? We haven't specified what A is. Well, I'm going to tell you what A has to be. So A, I'll write this over here. A has to actually be a value that normalizes this function. We need this function to be normalizable. So that means if we take the square of the function and then we integrate it over this domain from 0 to a, we need it to be equal to 1. That is normalization. So to normalize this, we have to make a equal to the square root of 2 over a. Now, I want you to try and verify this. Try taking the square integral of this, and I guarantee you will get this value as a. So this is the value of a that guarantees the area under the curve of the probability density function that you get from this wave function. That has to be equal to 1. So that's just from the normalization condition. And the reason we have a square root over here is because we're taking the square integral. And then we have to take a squared. And that's why we have to square root it afterwards. So the square integral of this is going to be a on 2. And to cancel that out, we need to have 2 on a. And then we get a square root because we're taking the square root after squaring it. So that is the process of normalization. So what have we done over here? We've started with the general solution to this ordinary differential equation that we got from the time-independent Schrodinger equation. And then we applied the boundary conditions. We got rid of this cosine term, and we managed to specify this k coefficient. And the k coefficient can only be these values, so values of this form. So now, what can we do? Well, we can actually write down the allowed energy levels. I'm going to do that underneath. Let's write down the allowed energy levels. We have a relationship between k and E over here. What I'm actually going to do is I'm not going to take k, I'm going to take k squared. And I'm always going to write this little subscript n because we don't just have one k value and one E value, we have an infinite set of these different values. So let's write that down over here. So let's take kn and actually square it. So we'll take kn squared. What is that going to give me? If I take the square of this value, I can just square this side over here. So that's going to give me n squared pi squared over a squared. So that is this value over here squared. And I can set that equal to the square of k over here. So I can set that equal to the square of this. And the square of this is just going to get rid of this square root. And it's also going to square the h bar in the denominator. So that's going to give me 2m. And for E over here, I'm actually going to write E subscript n. So this is not just any energy level, but this is the nth energy level, because this is the kth value, or the nth value of k over here. So I'm going to divide that by h bar squared. So this is an equation we've established. This has come from the boundary conditions, and this has come from this definition up here. So now what I'm going to do is I'm going to write this as a function. I'm going to put en on one hand side. I'm going to write all of these other guys over here. So I'm going to write en as a function of kn. So I'll do that right here. So we have en. That's going to be equal to, first, I'll consider this function over here. I'm going to take h bar squared times kn squared. And I'm going to divide that by 2m. So we have h bar squared, and then we have kn squared, all divided by 2m. So that's one form that we can get from this equation. Another form is we can take this term over here and this term over here. We can multiply this, and that's going to give me an h bar squared over here. So I'm going to get n squared, pi squared, h bar squared, and all of that is going to be divided by a squared, and we're going to have 2m. So I'm going to write 2ma squared. So have a look at this. We have gotten n squared from here and pi squared from here, multiplied by h bar squared, and have divided by 2m. That's giving me 2ma squared. So this form over here looks very familiar. You can think of this top part as the momentum. This is analogous to the momentum. So this is the same as the kinetic energy in classical mechanics. We have p squared over 2m. Now that should be very familiar because that keeps showing up again and again. And in Hamiltonian mechanics, we like to write the Hamiltonian in terms of the momentum. So you'd have p squared over 2m as the kinetic energy term. So we don't have any potential energy because inside here the potential energy is 0. Outside the potential energy is infinite, but inside it is 0, so it doesn't actually appear here. So this is just the kinetic energy term. And this is an alternative way of expressing the energy. Here the energy is actually written as a function of n. So here it's written as a function of kn, and here it's written as a function of n. And you can see the dependence over here. It's a quadratic dependence. So for the nth value, it's going to go up quadratically. And these constants over here, these guys are all constants. Pi is a constant, h bar is a constant, 2 is definitely a constant, the mass of the particle is not changing, and the size of the box is not changing. That is A. Now, what I'm also going to do is I'm going to write this in a slightly different form, because sometimes you're going to see this written in terms of h bar, and sometimes you're just going to see it written in terms of h, which is Planck's constant. So what I'm going to do is I'm going to unpack this a little bit. I'm going to take all of these constants to the left-hand side over here. So n squared, pi squared, and we're going to divide. We're still dividing by 2ma squared. But I'm going to unpack this h bar. So h bar is the reduced version of Planck's constant. And that's actually equal to h over 2 pi. So we have h over 2 pi. And this is still squared, right? Because we're squaring this guy. So we still have all of these constants. N squared, pi squared is there. 2ma squared are all in the denominator. What's going to happen when I square this? I'm going to get an h squared in the numerator, but in the denominator, I'm going to get a pi squared. And this pi squared is going to cancel with this pi squared. So we're going to have pi squared in the top and in the bottom. What about this 2? This 2 is also going to get squared. It's going to get turned into a 4. So we're going to have 4 times 2, which is 8. So I'll write that out in full. We're going to have n squared. This pi squared has disappeared because it's cancelled with this one. We're going to have h squared, and then we're dividing by 8ma squared. So we have 8ma squared. So nothing has happened to the a squared or the m, nothing has happened to the n squared, but the pi squared has disappeared, it's just cancelled, and this 2 has been squared, it's been turned into a 4, and 4 times 2 is 8. So this is an alternative way of writing the energy. So the energy is still has a quadratic dependence on n, which is that index, but all of these other guys are constants. And we're actually going to use this expression in the next video when we generalize the particle in a box to 3 dimensions. So I just wanted to write this out because this is a common way of writing it. These are the 2 common ways of packaging up all the constants. Sometimes you do it in terms of h bar, sometimes you do it in h. So it's a different way of packaging where the 2 pi's are going. This expression does not have any pi's. This expression has a pi squared. Okay, so now we have the energy written down. We have an expression for the energy. In fact, we have several alternative expressions for the energy. So these are the nth energies that are allowed. These are the only allowed energies. You can't have any other energies in between. So that is, again, linking back to quantization. This is quantized energy. So you can't have any continuous value of energy as you would for a free particle. A free particle can have any allowed energy. Or a classical particle in a box, it can have any possible kinetic energy. But the particle in the box in quantum mechanics only allows a discrete set of energies. And those discrete set of energies are given by this n subscript over here. So this n is an index that tells us all of these discrete values that are allowed. And it multiplies all of these constants. So we have the energy and we have the eigenfunction. So I'll write down the eigenfunction explicitly because I've just written the normalization factor and this over here. So I want to write down the eigenfunction, so the solutions to the time-independent Schrodinger equation. So what is the nth solution? I'll write that down underneath. I'll write it in green. So what do we have? We have psi of n as a function of x. This is the nth solution to the time-independent Schrodinger equation. This has a normalization constant, and that normalization constant is 2 over a. And then the function is a sine function, and it's sine of kx. But k, or k sub n, is actually just equal to n times pi over a multiplied by x. So that's what we have. This is just a sine function. And this combination over here, n pi over a, that is just equal to k sub n. So this is the nth allowed value for k. And that actually specifies the nth eigenfunction. So this over here, this is a stationary state, if we think about this. So if you begin the particle, if you initiate the system in one of these wave functions, it's just going to stay in one of those wave functions. And it's going to have an associated energy that's given by this equation over here. So an E sub n, the same n that's associated with this n over here, that is the associated energy with this eigenfunction. What about the general solution? What about the most general possible solution? How can we describe the time evolution of this system? So we're not always going to be very lucky and start the system in an eigenfunction, right? Usually we're going to start the system in some random combination. But the beautiful thing is that these guys are mutually orthogonal and they're complete. So mutually orthogonal means that if we take the inner product of two of these guys, we're going to get the Kronecker delta symbol. And the Kronecker delta symbol is going to be equal to 0 if the subscripts are not the same. And it's going to be equal to 1 if the subscripts are the same. So that is the property of mutual orthogonality. These guys are mutually orthogonal eigenfunctions. And the fact that they're complete means that we can express any other function, any other allowed function, in terms of these guys. So we can just build them up in terms of a linear combination. So let's do that. Let's take a linear combination of these guys and have some coefficients. That's going to give us the most general possible situation. And then what we're going to do is we're going to multiply this by an exponential function. And that complex exponential is going to take care of the time evolution. And we've covered that in earlier videos in this playlist. So underneath, I'm going to write the most general possible wave function and how it depends on time as well. So over here, I've used a lowercase psi. For this general wave function, I'm going to use a big capital psi. So big capital psi, and psi, it's not going to be the nth value, it's just going to be the wave function of a particle, and it's the most general possible wave function. And this psi is going to depend on position, and it's going to depend on time. So this is going to take into account the time evolution of the system. So this is going to be equal to, we're going to need to take a linear superposition, right? We're going to take a linear combination of these guys. So let's do that. We're going to need to take a sum. And this is going to be a sum. Why are we taking a sum and not an integral? It's because there's a discrete set of these guys. There's an infinite number of them, but they're discrete. You have this index n that tells you exactly what energy level is associated with what eigenfunction. So it's not a continuous spectrum, it's a discrete spectrum. That's why we're taking a sum and not an integral. When this turns continuous, this sum is going to turn into an integral. But because this is discrete, we're just going to have a sum. So this is going to go from n equals 1 to n equals infinity. And we're going to need some coefficients. I'm going to call those coefficients c sub n. So this is the nth coefficient of one of these functions. And I'm going to switch colors to green just to make sure that we're taking into account that this is the eigenfunction. So this is the same eigenfunction. I'm going to have this normalization constant, 2 over a. And then I'm going to multiply it by this over here, this sine function. So we have sine of n pi over a times x. And you can see that the units work out because x has units of length, that's the position coordinate, and a also has units of length. A is the length of the box. So the lengths cancel out, we're just left with n times pi. So now we have this guy over here, but we're missing something. We're missing something very important. We're missing the time evolution. Remember, this depends on position and time. So we've taken the linear combination of these eigenfunctions, or these stationary states, but we have to take into account what happens when these guys change over time. So we need a time evolution function. So that's going to be taking care of the complex exponential. So we need e to the minus I, and then we're going to have the energy over h bar. And the energy function that I'm going to use this expression for the energy. So I'll substitute this over here with h bar. So I'm not going to use this one, I'm going to use the h bar one. And I'm going to put that in brackets. We're going to have n squared pi squared. And this is not going to be h bar squared, it's just going to be one factor of h bar. Because I need to divide this by h bar to make sure the units work out. I'm going to divide this by 2ma squared. And this is going to be multiplied by time. So we have a complex exponential, and this over here, this is just the nth energy level, the nth energy value, it's an eigenvalue, and we're dividing it by h bar. Because h bar has units of energy times time. And if you have something of units energy times time, and you're dividing by it, it actually makes the units work out. Because over here we have an energy times t. Energy times time, well, that has the same units as 1 over h bar. Or it has the same units as h bar, so when we divide by h bar, the units cancel out. So we don't have this as a unitless quantity when we're putting it inside the exponential function. It's the same story as this sine function over here. We need the units to cancel out inside the brackets so that we can take a unitless quantity and we can take the exponential of that or the sine of that. So that is just making sure that we have dimensional consistency. So all the dimensions work out. So this is the time evolution function, or the time evolution operator that's acting on each of these eigenfunctions. So each eigenfunction has its own complex exponential that describes its time evolution. That's why this n is here. This n is specifically associated with this specific eigenfunction. And this coefficient is also associated with it. So all of these guys are associated with a specific stationary state. And the stationary states are these eigenfunctions. So if you were to prepare the system in one of these states, then you wouldn't have any time evolution. You'd still have this complex exponential, but what would that do? That would just be winding around, and it wouldn't actually change the amplitude. It wouldn't change the probability density. So the amplitude would still be the same. And if you take psi times psi star, that's going to give you the probability, and that is going to remain constant. But if you take a superposition of them, they're going to have different complex exponentials. So these different complex exponentials are going to be winding at different rates, and they're going to be mixing together. So in general, you're going to get some wobbly mess. There's going to be a wobbly mess. So that is actually the most general way we can describe the wave function for the particle in a box. And we're going to be using this in later videos. And you can actually try and simulate this. You can try and go online and find some graphing software, and you can work out what this wave function is going to be doing. You probably don't want to graph the wave function then. You want to graph the probability density function. So ideally what you'd want to do is you want to take psi and you want to times it by psi star. So times it by the complex conjugate. And then you're going to get rid of all of these imaginary numbers over here, and you're just going to get real numbers. And you're going to get some kind of graph that fits in between x equals 0 and x equals a. This red curve that I've drawn over here actually corresponds to n equals 1. It is this function when n equals 1. So it's half of a sine function. This is the ground state. It's the ground state of the particle in a box. And if you prepare the system in the ground state, it's always going to stay in the ground state with the ground state energy. The ground state energy is just what happens when you set n equals to 1. So when you set n equals to 1, that's just 1 squared, and that's going to, you can just ignore this n. That is just these constants over here. Or alternatively, if you ignore this n, it's these constants over here. That is the ground state energy. That is the energy associated with this eigenfunction. And that's why that's called a stationary state. In fact, if you took the time evolution of that stationary state, what you would get is just a winding around. So this function would wind around in the complex plane. So if you imagine there's a complex plane, if you took this into the third dimension, you'd have this winding around the x-axis. And that winding would not change any of the amplitudes. The amplitudes would remain the same. And so if you took psi times psi star, which is the square of the amplitude, that would give you the probability, and the probability would not be changing over time. And that's why these guys are called stationary states. But in general, your solution is not going to be a stationary state. If you prepare the system in any arbitrary state, it's not guaranteed to be a stationary state. It's guaranteed to be a linear combination of stationary states, though. So you can take some constants, these coefficients, and multiply these eigenfunctions together, and that's going to give you the general solution. So how do you actually find these constants? Well, that's actually a little more complicated. You have to do some interesting tricks. So let's consider what would happen if you set time equal to 0. If t is equal to 0 over here, what's going to happen to this expression? Well, this is not going to change. This is still going to be the same. But this complex exponential is going to have 0 up here. So that's going to turn all of this equal to 0. You're going to have e to the 0, which is 1. So this disappears at t equals 0. So at t equals 0, you don't have any of this complex exponential business. You just have this linear combination of eigenfunctions. And what you want to do is at t equals 0, you want to find what these coefficients are. You want to find these coefficients, and those coefficients are going to uniquely describe the initial conditions, or the initial state of the particle in a box. So that's how you prepare the state. Then this time evolution is going to tell you what happens to the particle as time goes on. So what happens when you're given an initial condition and as the particle evolves over time? That is what we get from the Schrodinger equation. That's what we get from the time-dependent Schrodinger equation, where we have the Hamiltonian operator acting on the state, and that's the same as the time derivative with some constants out the front. But this guy over here, this is the time-independent Schrodinger equation, and that's what we used to find this eigenfunction. So I'll give a quick little summary of what we did in this video. So let's have a look at what we did. We took the particle in the box, we described the potential, we used the time-independent Schrodinger equation to find this ordinary differential equation. Then we found the general solution, we applied the boundary conditions, and that fixed us to a value of kn. So these were the possible values of k. We then used this relationship for kn to find the nth energy level. So this in general is all of the allowed energy levels. And we came to the conclusion that the energy levels are discrete. There's a discrete set of energy levels that are allowed. You cannot be in between those energy levels. And that's where the quantum in quantum mechanics comes from. And then what we did is we wrote down the eigenfunctions. So these are the solutions to the time-independent Schrodinger equation. And we took a linear superposition of these guys. We took a linear combination, which is also known as a superposition of these guys. And we had coefficients called Cn, and those guys gave the general solution. And we also introduced this time evolution operator for each of the eigenfunctions. And this is going to tell you the time evolution, or the most general time evolution for the most general possible state. Any possible initial condition that is physically reasonable is going to fit in with this formula. All you have to do is find the coefficients at t equals 0, and then you have the entire time evolution until you perform a measurement. The moment you perform a measurement, this goes out the window, and you have to start off with new initial conditions. So hopefully this is helpful. In the next video, we're going to be generalizing this to 3 dimensions. We're going to have a look at the 3-dimensional particle in a box. And you can find that if you click on the link to the quantum mechanics playlist.